Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Right, so I'm going to start. It's my pleasure to introduce Yima today. He's giving a very interesting talk. Yima is an associate professor from UIUC. He obtained his PhD from UC Berkeley back in 2000. Yi has won the Ma Prize in '99 and the Longe-Higgins Prize back in 2004, is it? Yeah. Yes. His interests span a lot of areas, but fundamentally he's interested in analyzing and understanding high-dimensional data to allow intelligent decisions to be made. So he has worked on things like multi-view geometry, segmentation, object recognition, statistics, and control. So today he's going to be talking about face recognition.
Okay, thank you very much. Thanks for for inviting me, giving me this opportunity to speak here today. So today I'm going to talk about face recognition via sparse representation. So as you can see, that face recognition has been a very active topic for many years. Recently it has cooled down a little bit. But sparse representation is very much on the rise, so it's a very hot topic. People say that the folks that study sparse representation are densely represented now in scientific communities. So it's sort of a combination of very cool application and some very beautiful piece of mathematics, sparse representation. And we'll see if these two get together, if we can inspire some sparkles that can help solve this traditional face recognition problem to some extent. So this joint work with my student John Wright and my former student Allen Yang, who's a postdoc at Berkeley now, and Arvind Ganesh, my current PhD student. John Wright actually was here last week. He actually got the Microsoft fellowships, and also primarily for this work. And you see that he's very much the driving horse behind this. So context, before I start, just give you sort of a context of my research. What I'm interested, at least one of my passion, is how to understand, to face this challenge of massive multivariate mixed data. So these days, video, images, gene expression, microarray, and in a more supervised scenario, that the faces, how to recognize faces, handwritten digits, or categorize images, right? So for various applications. So in here, and this domain is more unsupervised, meaning that if I just give you this data, try to figure out what the structure of the data. And can you represent it more compactly? Can you compress the data? Can you find the structure? Find the information encoded in the data. So that's one of the problems. Here is sort of a supervised scenario, meaning that you can pre-collect, in priori, the sum of the faces that you want to recognize by your computer, or digits, or handwritings. Here's the same thing. You can make the machine to learn something about what you try to recognize. It's sort of supervised or semi-supervised scenario. In any case, both problems, either you're trying to cluster them or classify them, you're trying to harness what is the structure in the high-dimensional, massive amount of data. Right? So that's the sort of a context. Some of my recent research is interested in this. So as Simbing suggested, I'm very interested in what class of mathematical model are the most relevant or at least easy to start with to model this kind of data, or to try to capture structure of such massive high-dimensional data. So one class of model we have been experimenting is just model the data, the high-dimensional data, as lying on a union of subspaces. So this looks very, very simple, right? It's almost the immediate class of models that you can think of. But turns out, mathematically, this is a very, very complicated class of object, either algebraically or statistically or analytically to analyze. And also, it's extremely powerful. You want to say that the reason being that it's not a manifold in the sense that you allow a different piece of your data to have a different dimension, different complexity, as we normally see with images or videos. Right. So now, obviously, there are two problems associated with this. If I want to use this class of model to model my data, one problem is that if I give you a collection of points, representing data in the high dimensional space, try to figure out how many pieces there are, right? So this is sort of a generalized PCA problem. Probably most of you know PCA, right? So you basically try to fit the data with a single subspace. Now the problem is much more complicated. You do not know how many subspaces. You do not know the dimension of individual subspace. And you try to figure that out by just looking at the data, right, at the computer. So this is sort of my work on, I have recently worked on this sort of generalized PCA scenario. And one particular approach is that turns out for this kind of data, because although the data is lying on very high dimensional space, but the actual structure is very low dimensional. Therefore, it's very compressible. So if you try the best to compress the data, to reduce the entropy, try to find the minimal entropy of the data, as a result, the correct encoding scheme will force you to break down the points, break down the data into different pieces. It will automatically give you the clusters. So that's one branch of my work recently is in that. So if you're interested in that topic, you can go to my website. There is a specific website dedicated to this topic. There has been some very interesting progress. And actually, this approach is generating the best image segmentation or motion segmentation results so far. Actually, far better than, arguably, far better than spectral clusterings. And today I'm going to talk about the second branch, which is that if I have data has such structure, how can I harness such structure to do classification, right? And people working with classification say, we can just using any generic classifiers like SVM or nearest neighbor, near subspace. Today we'll see that if you use the information correctly, if you can customize specific clustering classification algorithm for this class of object or structures, you can get much, much better performance than a generic classifier, right? That particularly applied to face recognition, we'll see. And also, keep in mind, precisely that your data lying on low-dimensional structure allows your data to have sparse representation. That's also sort of a hot topic these days. And also, precisely because your data has a low-dimensional structure that allows you to take much fewer measurements to recover the location of each point there. You don't need that many coordinates as originally presented to you, right? Hence, enabling compressive sensing. So I will mention that later, at least in the context of face recognition today. So give you a flavor of that. So why this keep? So that's face recognition. I did a little bit media survey on what happens after 911 with face recognition, right? So right after 911, Pentagon panicked, just tried to order anything that can be useful for terrorist attack, to anti-terrorist. So they actually, face recognition obviously one of the very, have high hopes. People try to make this work, to detect terrorists. But actually, ACLU is very cool about this. Actually, they actually predicted, at least at the time, the face recognition technology is not ready. Right? But yet, despite that, the stocks for some of the face recognition companies went through the roof, right? Doubled up within a couple of months. And they get a lot of fundings. But then after careful testing, actually, Tampa police, for instance, ran the system for 3 years. They couldn't get a single positive identification. In fact, they get a whole bunch of false positives. So arrested a few cases that got themselves in hot water, right, for that. As you can see, and then one particular news I liked a lot is that the smiling Germans ruined biometric passport system, right? So basically people have an expression when they go through the custom, custom actually, the system failed to recognize it's the same person, right? So that's sort of, but since come around, and so in last couple of years, UK or US start looking at the face recognition again, probably more seriously. And also there's a couple of papers suggesting some positive news. The PAMI paper, face recognition systems, the past human matching faces, and also the recent science papers, which turns out to be exactly opposite to what the title suggests. but it says 100% accuracy automatic face recognition. Right? Cause all this hype about this. What I'm trying to do here is that if we tend to exaggerate the performance or anything, that we quickly lose credit if we cannot deliver. Right? That's probably the case with face recognition. If we keep doing that for a few more times, we're going to lose. This kind of article doesn't really help the general public to understand what is the current status of the problem. So we'll see at least. So from my perspective, I'm more interested in what is the interesting mathematics behind this problem. Can we isolate some interesting problems? Face recognition is a very comprehensive task. Still, I don't see an obvious solution yet. But at least we can isolate some of the components, can give very deep, careful analysis. Hopefully, we can learn a few lessons. Can give us suggestions how can we build a more reliable, more robust face recognition system. So that's the topic of today. So especially, I'm trying to deal with face recognition when the images are either corrupted or occluded. So we will see random corruption or occlusion, and also see which face regions are actually more informative, and how do we recognize faces despite disguises by sunglasses or scarf or different type of disguises. And also that using the theory of sparse representation, we'll try to explain how to select training data. So far, many of the paper I have read about face recognition just choose the training almost arbitrarily from the existing data sets, AR database or Pi database. I pick session 1 or 2, I test it on the other sessions, so on and so forth. Why? Nobody tends to explain why. Most of the reasons are sort of heuristic, right? So I think this is enough. I think this is sort of challenging to do.
Just the reason because the why has a reviewer is asking for.
Yeah, well, probably. And also that finally, I'll touch upon this issue with feature selection in the context of compressive sensing. That again, there's a tremendous amount of work on what features are important. If you look at the literature, Eigenfaces, Laplacianfaces, Fisher faces, ICA faces, all kinds of faces flying around. Which one is better? Can we actually reach some consensus here, or at least in some well-defined conditions? With some well-defined conditions, can we reach some consensus there? So here's the setup. I think most of people here probably are familiar with. Essentially, that we're going to use the fact that the image of the same person under varying illumination lie approximated on the no-dimensional subspace. This is the work attributed to people study harmonic analysis of Lambertian surfaces under different illumination. It's an approximation, but it's very, very good. So arguably, it's either 9-dimensional or 7-dimensional, depending on actually what you're looking at in terms of how well you want to approximate the images. So that will be the assumption we make. Suppose I give you an image of the same person, that you have a collection of training image of the same person, K of them, K images of one person for the ith person. So if Y belongs to the ith person, you can write it down as a linear combination of them. Right? There is alphas. You can write down in this way. So this is when you know which person this is. Right? If you don't, if you only know that this person is one of the guys in your database, suppose you have n persons, right? Each one has a set of training data. But at least you know that it's one of this person. Therefore, one of the beta is not 0. So one of the beta will, if you write a linear combination, you'll be able to explain the testing image. Why? Question?
Are you making, when you say you make this assumption, are you restricting your problem to people just with the same expression and the same head position?
Yes, I'm actually mostly making the assumption that it's a frontal view.
So
yes,
it's a frontal
sorry,
view and one fixed expression.
Expression, we'll mention that later. You can handle expression fairly well.
Okay.
So
But
frontal view is important.
Okay.
And we have some existing work, ongoing work on poses as well. So we're waiting Pi to come out, extended Pi to come out. So try to do more extensive testing. But so far, this framework, the linear assumption only applies to frontal face, either under illumination changes or expression changes. So approximately so.
Other comments. And if K there equals to the number of pixels, then of course we can represent bananas just as well,
Yes.
right?
Yeah, we'll
And,
get to that soon. So.
And also, if you happen to add to your database samples from the pathological, people cut in two, right? So, you have half of one person, half of two. You can have them as a linear combination, which may be.
So no. If it's a linear combination, it's not. We'll see. Yeah. So in the end, maybe towards the end, that if I'm still not clear on what this model is capable of, and we can have further discussion on that. Right now, I think you're probably jumping ahead because a lot of questions maybe get answered towards the end, later part of the talk. So essentially, it's a very simple fact, right? So I'm not doing anything deep here. It's just that I have a test image Y. I can just write it down as I collect all my training data. I'm not doing any processing, just collecting each image as a column of a matrix, just to stack them for each subject, A1 to AN. Now I know that if Y belongs to one of the subjects, it can be written down. There is a solution to this equation, Y equal to AX. X has this format, right? One of the beta is not zero. The other ones are all zeros. That is one of the solutions, satisfy that equation. I'm not claiming that's the only solution to that equation, but this is the one I would desire to find out from this equation. Question?
Just curious, so if this is what you want, then what's the advantage of using a linear combination? Just to have to handle noise?
Right? To what? You mean
you want to do selection. Why do you need a plus there?
Why do you need a plus of what?
You see that you can just find a close one.
Yeah,
we'll see that. I say some of the questions are really jumping ahead of this. For now, just take this, this. Yes, I'm probably doing things redundant, but we'll see later on why this redundancy is important, is necessary, right? So that's actually the reason. That's actually one of the reasons that the paper was rejected by ICCV, precisely for the same reason. This is the first equation in our paper. They look at this, says this is not reasonable. They throw away the paper. But now the paper was accepted by PAMI, so we'll see why. After more careful review, you'll see the reason why. Hopefully today's talk I'll try to convince you that's actually absolutely necessary to do that. So there's big differences if you don't do that. If you do near subspace or if you do just a global representation. So anyway, for now, we're really trying to find one such sparse solution. A lot of entries of x at 0. The one that we really want to concentrate the solution x to have non-zero coefficient concentrate on one subject. That's really the goal here. So it tends to tie the solution to a sort of a sparse representation. But of course, that's the case if I give you a very clean test image y, right? So it's just pure linear combination of the training data. But if I give you a picture like this, try to find this is just the 16 people. So is it easy to do? Find out which person this is. It's actually this one. So but computer can do this very quickly. And also, in a newspaper, people try to hide the identity. They usually put a black bar on this. But turns out for computer, you can actually recognize the face very, very well now. For human, actually, it's very challenging. But for computer, you'll see that the technique that I'm talking about today is going to give surprisingly good results. And also, of course, more natural occlusion is like this, right? You wear sunglasses, try to recognize which person this is. If that's easy, try this one, right? So do you know if that's a face at all, right? So this is about 50% of the pixel randomly cropped it, and computer will see how well computer can do with this kind of results, and against a training set like this, so it turns out both faces are the same person, this woman. So you can actually do that. It's very challenging, actually. When we write the paper, we constantly make mistakes when we try to pull out which face is which. We're trying to crop to the face.
Illumination from the bottom right? Is that correct?
Which illumination?
There's a highlight on the hair left cheek, which is on our right side. So this is what you recognize as me?
Which one?
This
one?
This is third column.
See the highlighting?
The third column is second row.
Yeah, the only one
that's right.
Well, so actually there's a lot of women have similar hairlines. So. A lot of women have similar hairlines. And actually this is just a 16 picture I picked out from a 100 database. This is a AR database. So
at the bottom left, you're corrupting only 50%.
Yeah.
But I think it's more natural to actually add noise as opposed to randomly picking 50% and corrupting them.
So noise and corruption, what I'm talking about here, is rather different. We'll get back to that later. So yes, corruption is really different from noise, small noise. Why? Because we'll see that. So there are several ways. Basically, each pixel, you can change the value arbitrarily, right? Go from 0 to 255. So there's several ways people try to tackle occlusion or corruption, redundancy. You want your image to be redundant, right? But nothing actually is more redundant than the original image, if you think about it. And also people try to, all the eigenfaces, if you apply like a global, holistic features for those images, they're going to fail miserably because arguably you convolve the image with the filter throughout the whole domain. Therefore, the people try to find features or filters that has a smaller support through ICA or non-negative matrix factorization, right? But if you think about this a little bit, but no feature is more, or parts are more local than the original pixels. So if you really want to go after for the locality, the individual pixels should be the most informative in terms of telling you which identity, which person this is. Sparsity, we see that in terms of identity of the person in the database is sparse. Also, the error that occurs on the image is also quote unquote sparse. So meaning that maybe there are only 1/3 of the image are corrupted, right? But we'll see how far the sparse can go, if we do the mathematics correctly. Maybe the error we can handle is not sparse at all. So that's something we try to convince you today. So if you try to formulate the problem before, without occlusion, we know the test image can be written down a linear combination of the training data. That's simple. But with occlusion, I have to add something unknown, right? Here, the assumption here is that for E, I don't know where it occurs. So if you know that is where the occlusion happens, like where sunglasses, of course you can cut it out. You just use the rest of the image, right? The computer is not supposed to know that. Second is that the error is gross, meaning that I can add another picture on it, and the pixel value changes at this can be very, very big. It's not a small, you cannot deal with, sort of dismiss it as a small Gaussian error, right? The variance is very big. And also it's sparse. Even here, you look as if the significant part of the image has been blocked. It turns out it's only occupy 1/3 of the pixel. So that's surprisingly relatively small part of the image were occluded. But of course, the problem is become this. If I gave you a Y, I gave you A, you try to find X and E simultaneously, satisfy this equation. Right? It turns out this equation in general that D is the number of pixels, A is the number of training images in your data. Right? So it turns out this problem actually not necessarily has a unique solution. You may have multiple pairs of X and E satisfy the same set of equations. Right? But traditionally, people try to deal with this kind of underdetermined problem, least square, right? So for instance, if you try to deal with minimizing the error, this is sort of, if you treat E as a Gaussian noise, this turns out to be actually the optimal thing to do, right? If E is a random coherent Gaussian noise, you actually end up with minimizing. This is actually the likelihood, right? Least square is the best thing to do. But if you apply to error like this, occlusion like this, so this is what X2 found out. This is against the database, right? There's 700 pictures. This is actually the correct subject coefficient. But you can see the coefficient is not sparse at all. You get X spread all over, right? Which person this is? It actually turns out this is not even largest. One of the largest is here, right? And also the error does not resemble at all what's going on here, right? It's just spread all over here. And this is reconstructing. The best you can do is least square. You can play other tricks. You can actually minimize in the two norm of X. You get similar results. Right? So one trick to do this, to realize that when I try to solve this equation, both X needs to be sparse, located on one subject. E also is sparse, meaning that only corrupt part of the pixels. So you can rewrite this equation as y equal to AI times XE. Put XE together as Q. So you try to solve y equal to BQ. Now, the problem here is that B has a dimension D times D plus N now. So it has more unknowns, X plus E, than the equation. Equation only have D equations. So this is an underdetermined set of linear systems. There's infinitely many solutions, right? The kernel space, the kernel is non-zero, non-trivial. So, but fortunately, we have an additional piece of information. We want X and E to be as sparse as possible. So therefore, essentially, I'm trying to look for the Q, not arbitrary Q satisfy this equation. I'm trying to find a Q that has minimum number of non-zero entries, the zero norm. Right? So it turns out under very mild condition, for underdetermined system like this, the minimum norm solution, the minimum zero norm solution is unique, actually. So the question is, find it. Turns out finding this problem, finding the sparsest solution to even a linear set of equations, set of linear equations, is NP hard. It's actually a nasty NP hard problem, meaning that it doesn't even allow polynomial time approximation algorithm to approximate it. So that has been proven a long time ago in the 1980s. The recent breakthrough of sparse representation is by Donahoe, work by Donahoe et al., is that to realize that if I'm not looking for any sparse solution. If the Q is sparse enough, so basically so Q would be considered sparse theoretically if it's less than 50% entries are non-zero, right? But I'm not looking for up to 50%. What if it's only 1%? What if it's like 1,000 entries, right? Can I solve this more efficiently? Turns out, yes, you can. Turns out, I mean, in this case, when Q is sparse enough, you can simply minimize in the one norm subject to this equality. And this problem is purely linear programming and convex and can be solved by polynomial time. Basically, the general problem is NP hard, but I took a very big bite out of that problem, meaning that if the solution I'm looking for is sparse enough, it is not NP hard. That portion of the problem is not NP hard. You can solve very, very efficiently. And turns out that is also the case. Most real problems took places. Most problems that you solve, that the solution indeed are sparse enough. As we said, under the assumption that the data, although has very high dimension, but the structure is very low dimension. That's precisely when it happens. So that's just give you sort of a picture of what is that explained. So there's a very nice geometry. Why this is related to a very cool polytope high dimension of geometry is that, so when you can solve for this equation, Q that is k-sparse, let's say Q has k non-zero entries. You look at the cross polytope. This is a one norm ball of unit norm one ball. It's not a sphere, right? It's not a ball, a two norm ball. It's a one norm ball. And look at the B, basically map this ball, this polytope, squash that into RD, reduce the dimension, basically project it onto another dimension. Now, so in this case, you can see that all the vertices are preserved, right? It's outside of the polytope. The edges are not. So it turns out, if under this mapping, all the k faces of this polytope gets preserved under this map, then any k-sparse solution of this equation can be recovered through linear programming. Basically, you only have to find out which k faces in this polytope that your solution lies on. So that's sort of intuition, why the problem becomes convex, why the problem becomes linear programming. Right? So, but unfortunately, if I gave you a B matrix, try to check out what is the maximum k that this is k neighborly, this polytope is k neighborly. That problem itself is NP hard. And also, it's a nasty one that you cannot even approximate it. Why? But we have a combinatorial algorithm to compute this. So in some of the results later we present, we're actually using that algorithm here. If you're interested, you can read our paper to attribute transaction information theory. So that actually, nowadays, I study the high dimension random polytope is probably the hottest topic in statistical processing these days and discrete mathematics. So just give you another, in the face recognition context, what we are essentially doing. So every subject, I have some training image given to you. Right? Think about it, put them as, each training image is a vertex of the polytope. So this is subject 1, 2, 3, so for instance. And then I basically just put them in a big polytope, normalize everything to norm 1, put them as a vertex of a polytope. Then, if I have a test image, all I'm doing is to project that to say which facet of this polytope the face lies on, the test face image lies on. That's all. So therefore, if the polytope is convex, the problem is convex optimization, the bottom line, right? And this is the difference. So if you do this, you can compare with if you do the L2. This is a solution you saw before. If you try to treat the error as a Gaussian noise, you get this kind of a solution. Now, once you do L1 minimization, this is the solution you get. As you can see, the solution is very sparse in terms of x. This is already very suggestive which person this is, has to be, right? And also the error now is much more localized. Keep in mind, the error not only corrects the baboon image, but also corrects this piece. See, imagine that the linear model we had is for convex Lambertian surface, but face is not convex Lambertian surface, right? The linear model actually does not hold everywhere because there's occlusion and everything. But because in this framework, we can't handle occlusion, therefore it will automatically correct what's going on, that the part that the test image does not see, right? And how do I classify? Then once I get this solution, well, classification would be easy, right? All I have to do, for instance, I know those coefficients associated with which subject. Therefore, all I have to do is that to pick out the coefficient that belongs to each subject, say which one approximates my test image the best after the correction, after the error gets corrected. That's all. So I compute that residue rather than the residue given by least square or other things. So then you end up with like 5-line or pseudocode for face recognition. All you do is that you collect all your training data into the big matrix, then append an identity matrix. Keep in mind, identity is trying to deal with the error E, right? That's all. That's a B matrix. Then you solve the linear programming problem, y equal to bq. This is a very well, you don't have to even program a single line. There's a more than enough online code for convex optimization or linear programming that allows you just to, with one line of code, you can compute that. And also then once you compute this, just correct your image by subtracting the error, then computing the residue against each class, each subject. Then you classify based on the residue. This, of course, I mean, I'm sure that people, smart people can design better classifiers based on the residue and also the coefficient using the joint statistics of them. But here is sort of the most trivial, easiest thing to do, right? Already give very surprising results. Let's say, I mean, at least on the baby experiment, on extended yield database, 38 subjects and session subset 1 and 2 for training, and the rest for subset 3 for testing. So we estimated that actually theoretically, you can handle 13% of errors, arbitrary errors. But keep in mind, that 13% is the worst possible error. So here we crop the image randomly. We pick 30%, 50%, or 70% of pixels randomly, and crop them each pixel randomly between 0 and the maximum value. Right? Has completely independently. This is the performance, and you can actually see that up to, I mean, as you can see, up to 50%, you don't even know this is a face, this is a human face anymore, right? But computer can do up to 50 or 60% almost perfectly. And even 70% is beyond 90% of recognition rate. Right? Here you don't even know who the heck this person is. And this is a recovered face with this much corruption. So it's dramatically surprising that you can actually even do this with a computer, right? And this is the other method, like PCA, ICA, or local.
Large noise is actually easier to handle, right? In this formulation.
Here we
for
have
us, it's hard visually, but
yes.
For the formulation, it's much easier. I mean, if you had infinity, it would be even easier, right?
Yeah.
So I mean, maybe it's not. I mean, there used to be a lot of work about random dot corruption, right? And in the 90s, or 80s, it was very big for a while. But it's not. I don't know if it's a useful
for nearest neighbor.
No, to show that you can use a random, complete random noise, and it's hard to recognize it visually, but it's much easier.
Yes.
Because for this formulation, I mean, you're just doing selection, right? So large error is much easier to avoid, right? I mean, how about you add to the top image noise to make it look exactly like the second image? That's also noise, right?
Oh yeah, I mean,
so
that's why you're looking at the performance on average, right? So you're looking at all kinds of.
It's not necessarily a useful test, for this. I mean, it doesn't help.
What?
And like Sing-Ming said, if someone sold you a camera that gives you that kind of an image, you just buy another camera, right? I mean, what's the point of that test, right?
No, this is just testing the performance of the algorithm under all kinds of conditions. We're going to test that a lot, right? So I'm not saying this is the only algorithm or the only experiment we run. So this is a more continuous occlusion. So obviously it's more challenging, turns out, as error correction. Especially the computer doesn't know where the block is, right? So for human, we know that. You can cut it out. But computer doesn't know that. So it turns out in this case, you can only handle up to 30%. You're already very close to the worst case, which is 13%.
I want to go a step forward as well. You use the monkey, which is great. But what if I went to one of those stores that can print a photograph on a cake, and I put my face and I print on it your face? Yeah. That's another way.
That's a different problem. As I said, what is really lack of in many of the research in computer vision or even in face recognition in particular is to try to isolate problem. Right? We're trying to. So we do not try to solve all the problems at once. I think we had this approach, what I call the compound and conquer. We try to compound all my factors into try to solve a problem. But yet the really more effective way in science has been practiced is really to try to divide and conquer. We're trying to just isolate a single problem. Let's say try to deal with the error. That can we formulate find the best mathematical tool to deal with it, and prove beyond doubt that has reached the limit of it. Then we can worry about other problems, right? If you have smile, pose, and so on. So we can deal with other things. Or deal with the situation you just described. Have a face printed on a cake or something. That's really not a problem. Under this assumption of the work you can handle, right? Or intend to handle at all.
Right? For each subject, how many images do you use for training?
In this is about 16 or 17. Later on, we'll show a lot of examples with much, much less training data with AR database.
Appears that you would need
7 or 9.
All the illuminations, right? In the training data, you better have for each subject you need
several,
image for every illumination.
Yeah, it turns out for illumination, actually, if you have a good location of light, 3 or 4 is actually mostly enough.
Yeah, you have
3 is enough for inversion, right? Because you just need to span the normals. Yeah. So 3 is enough for the inversion surface. But
no, for 3 is not enough. It is
for the inversion surface, it's enough.
So here's one reason that one situation why you wanted to do computing the linear equation globally, not to individual subspace, not to individual subject. So you wanted to validate. So if I gave you a face which is in the data sets, obviously the solution is very located. If the person is not in the database, the solution will look like this. So you wanted to reject it as invalid. So you have to look at the ROC curve, right? So the surprise actually comes from there. So if you do global one minimization, keep in mind we're actually computing the X against all the training data for all the subject. So you're actually using the joint statistics, joint distribution of all the subject available to try to determine if a person is in this database or not, right? If you just do this plus near subspace, one subject at a time, this is the ROC curve you get. But the red one is use a 1 plus sparsity. Just that simple rule, basically, if the location, so the maximum, if the coefficient located on one subject, one of the subject is above 8 lambda, above tau, we actually accept it. Otherwise, if all below this one, like this one, we just reject this. This is invalid. Basically, the solution is gets spread all over the training data. So it's a very intuitive rule. Of course, you can come up with a better one, but already this one works surprisingly well, even up to 10% of occlusion. The ROC curve is I've never seen ROC curve like that. So it's almost unbelievable.
Well, almost a comment, but it seems like the most relevant thing to compare with is there were, like in the 90s, the robust eigenspace approaches like Leonardus and Bishop.
Yeah.
It seems like this would work better, I'm pretty convinced. But
yeah, we have
those optimizations simultaneously.
We have actually, in fact, one of the best work, just a couple of years, published in PAMI, using that robust PCA to do face recognition, was, I forgot the name, it's 2006 paper, using actually random sampled pixels to estimate the eigenspaces. Exactly. Similar idea, but they have to rely on random sample techniques, which is really the performance you cannot really guarantee. Here you can use the sparse representation to guarantee the performances. And also that later on I'll show you the experiments on AR database. that the number is actually much better than the number they put up there.
Right. It would strengthen your results if you compare.
Yeah, we did. In the paper we did. So in the paper we did. So here I just picked the norm one, the baseline one. So we didn't compare with all this more sophisticated method. But, to be fair, the algorithm here we presented is as simple as, probably simpler than most of the other techniques. Right? There's no free parameters to tune here.
No, right, but that's.
So and also you can
explicitly try to estimate the occlusion method, right?
You can also estimate which part of the face is more. It turns out actually it's not that big difference. Nose, mouth, eyes. There's a little difference, but it's not as dramatic as human vision. We noticed. In the human vision literature, there is dramatic difference. If you occluded eyes, nose, or mouth, human can recognize rather differently in terms. But computers is not so discriminative. As long as there is information, it will find it. And also, this is for AR database. Now we're testing a more realistic situation. Here we only have 7 training, or actually 8 training data. Also, the training with expressions. There's much more challenging. There's more subject. It's 100 subject, and not only there is the 19 condition expression, but also there's occlusion. It's a much more challenging task. So here, of course, you can see the performance drops dramatically from 100% to 80 or 60. But keep in mind that here we do have information. If you know that your occlusion is continuous, you can try to use that information in your designer system. You can break down the image into parts, small blocks. Here we just break down into 4 by 2. Then you can just run the same algorithm 8 times, right? But for each block, make a vote on the person. Now you can see the performance gets boosted up nearly perfect, actually. In fact, those are we actually have better numbers even than this one. It's very hard to beat even the basic algorithm. With a little bit of tweak, you can get this number even higher. So for men, the 50 men that we tested with sunglasses actually get 100% recognition rate. Woman is consistently harder to recognize. We don't know why, because maybe they want to make themselves look similar to each other, use a makeup. There's another thing that now with the mathematical theory, now you actually can see what may be right or wrong about your training data. What the training data is easy to, good for occlusion. If you want your face recognition system to be robust, now the sparse representation tells you the breakdown point between L1 and L0 is a good index to look at. Now, if we did this for ELB, if you just for training set 1, the breakdown point is 1,124 pixels. Here is much higher. Basically, if you use more extreme lighting in your training, the polytope likely to preserve more faces, can handle more occlusions. The same thing with expression. You can actually compute. Normal face plus happy give you the highest breakdown point. Basically, your algorithm guaranteed to work up to that number of corruptions. So the worst corruptions. But if you have, the worst case is that happy, the normal and angry. I mean, I cannot even tell the difference, right? So, but basically, this is actually a observation from coding theory, information theory. When you try to code your data, the more robust you want to be, the more incoherent the dictionary needs to be, right? So that can have more power to extrapolate, to interpolate. So enough about occlusion. Let's worry about a little bit about the features, right? So if I don't have occlusion, obviously I want to use the minimal number of measurements to do recognition. So can you recognize which person this is? If this is human can do from extensive psychological study that even for famous faces, human can do up to 16 by 16 pixels. Or number changes, or depending on which paper you read, 14 by 18. Basically, it's around that range. Like Clinton or Lincoln, you can recognize with that resolution. But maybe for your family, you probably cannot. But this is just 120 pixel, and this is a 120 random pixel, random projection. Basically, you just take a random subspace onto project your image onto that. That's what you would get. This is 120 eigenface. So now you know which person that is, right? It's this person. It's very hard. But turns out, we'll see that in the feature selection, what the problem is, we had originally, if I have full resolution, is y equal to ax, to try to solve the L1 minimization problem. Now I'm trying to use much less measurement, project everything through a matrix R, are representing either the downsampling matrix or the random projection or the eigenface transformation, right? It's a linear transformation. So reproduce, just reduce capital D to little d. The recent work on computer sensing actually suggests that it's actually, in order to recover x, which encodes the identity of the object, it's actually the number of linear measurements is more important than the specific details, how those measurements are constructed. Turns out there's a most recent work by Donovan Taylor says that there's a phase transition behavior. If you have your number of measurements just above that threshold, with overwhelming probability, you can recover solution perfectly. Below that, forget about it, right? So the question, of course, in face recognition is that does the data-dependent features, well, here they are studying random polytopes, random data matrix. Here we actually has very specific data matrix. A is given to you, right? These are those faces. Does those faces has the generic structure predicted by the compressive sensing? Do they actually give, neighborly polytopes? So this sort of just come back again, why L1 actually, again, works, even just for recognition classification, works better than near subspace or nearest neighbor. So here's that you do L1 minimization, solving that problem. This is the coefficient looks like this. Using 12 by 10 pixels. Here, as you can see, this is located correctly on the first subject. That's where this person is. This is the residue if you do nearest neighbor. It's a mess, right? So basically, you're trying to find the minimum of that. Most of the time, you find the right person, but many times you don't. This is the residue you compute using the L1 coefficient. Most of them are huge, except this one, right? This is the residue that you compute near subspace, right? As you can say, well, in this case, it's still the right person. But I would ask you to prefer which one if you want to say which one is more discriminative, right? Comparing. That's why you'll see that performance-wise, in a minute, that why L1 performs much better in terms of classification than near subspace or nearest neighbor. Precisely because it actually has a tendency, L1 minimization actually regularizes your solution so that it has a tendency to not overfit. So either nearest neighbor or near subspace actually overfit your data, especially if you imagine that your data, this is your face images. They span subspace, all right? But within the subspace, it still may have structure. Like your lighting condition is changing or expression is changing, right? Like this one. They're changing in both directions. Now, if I have a point here, if I just run nearest neighbor, or near subspace, it will claim that one is in the same subspace, therefore will classify as that person. But L1 will not, because it will actually only points close to this local linear structure will get classified. This one will rule out. This is not the same person. So as you can see, L1 actually will use just to strike it, just to think about the L1. There's nothing really special about it now. It's just to strike a balance between nearest neighbor and near subspace. Near subspace uses all the data in each subject to represent the test image. Nearest neighbor uses the nearest one. L1 will pick the minimum number, just enough to represent your test image the best. It will automatically do that for you. And you pay a little price to do that. And you can see now, you can actually compare all those features, Eigenfaces, Laplacian faces, random faces, downsample faces, feature faces. So this is on the feature dimension. As you can see, after 100 dimension, all the algorithms converges very quickly. Even the actually random faces turns out to be the best. Of course, there's a couple of conclusions that, so other methods, if you use SVM or nearest neighbor or near subspaces, even after that dimension, it doesn't really converge very well. I mean, for those classifiers, choosing the right feature do make a difference. Does make a difference. But if you use the compressive sensing, use the sparse representation, it doesn't. So you actually boost the performance. Not only that, it makes all the features converge very, very quickly. Meaning that the information about the identity of the person is already there, even in the downsample image, even in the random projections, right? And if you force yourself, work with the domain below this region, if you force yourself to work below this region, then feature selection is still a very relevant issue. As you can see, the feature faces always works much better than others. So basically, if you force yourself to use very, very small, tiny set of features, fine, go ahead and find the best one. For every data set, maybe there is one. But once you use just enough, not that many, probably by that formula is actually very, very small. It's logarithmic of the number of subjects. It's very, very few measurements. You can already get a convergence of performance. So those are just numbers. I mean, the same thing with AR database. We tested on AR. We're still waiting for the extended pi to come out so that we can check the scalability further of the algorithm. But basically, the conclusion is very much consistent. We have run many different databases. And also, you can run on different parts of the face. As you can see, it turns out if you have at least in the frontal face case, choosing the parts really doesn't really help too much. As long as you have enough measurements, support. As you can see that even I just using the second half of the face, I can still achieve very, very, very high recognition rate. Even if I use eyes, but if it's small version, a smaller number of measurements, but actually the performance may suffer. So this is the, but in any case, that you will see that one is able to harness the no-dimensional structure much better than other generic classifiers. That's the bottom line. As you can see, it's not that easy. Those are the test images. Can you tell which one this is? Right. So this is under different lighting conditions. The right eyes looks like that. So it's actually pretty challenging. The test is not so trivial. So just to conclude my talk, here we make a big assumption. This is exactly the problem I'm trying to isolate out of the face recognition, is that we make assumption. There are situations like if the face is under lighting condition changes or expression, you can roughly model the face image of the same person as lying on no-dimensional subspace. Under that assumption, we have seen that we can use the sparse representation to design customized classifiers, which works much better than the generic classifiers. Also, occlusion can be dealt with very elegantly and unified in a unified way. And the results actually quite surprisingly surpass human capabilities, right? Before this, we have read papers about human vision, how human vision is always generically better in terms of downsampled images or in terms of cropped images. Now we try to beg to differ. Also, the algorithm is scalable. In fact, most of the algorithm is linear programming. They are actually is linear in the size of the data set. So it's actually not that slower than near subspace or nearest neighbor, if you do it correctly. And also, it suggests at least some useful index for selecting training data. There's many implications that either holistic versus local feature. I mean, at least in the frontal view case, lighting condition expression, we don't think there's any dramatic difference. But with pose, yes, indeed, choosing the right feature might be an important issue. And also, at least in frontal case, we don't think that you actually should. It's necessary to use a 3D model. And of course, we hope that this method may be useful for other classification problems. I'll mention a few other applications just in a minute. Whenever the linear model, if your data has a low-dimensional linear structure, you should definitely give this a try. And there's many, many future problems. Actually, in fact, this actually opens more problems than actually solved. Is that choosing the best training data set? So far, very little study has done. Most studies that even the way that data gets collected are very much handled in an intuitive way. Now, there are some mathematical tools that allows you to compare different data sets, how much occlusion or how much they can extrapolate. And also that we see the performance. So far, the compressor sensing and sparse representation, the bound given us for the worst case, basically the worst error the system can handle. But in fact, we see that in the face recognition, we can handle the random corruption up to 70% or 80%, actually in some situations, very easily. Why? There is not a theory to explain that. There's still ongoing work. And also that with pose variations, obviously, how much of this work can actually apply there? We're still working on that. And also combine recognition and detection together. Right? Here we sort of assume our face are frontal and well aligned up to several pixels. The algorithm is robust with respect to few pixels because it handles occlusion. So if you have a little bit of misalignment, it actually works very well. But what if you have detection, recognition together? So basically, there is going to be a fundamental trade-off. Nobody understands yet, at least I don't see any work, between false positive and robustness. So if I want my system to be very robust to occlusion, So I have a tendency to accept more faces gets identified as one of the person, right? It's sort of natural, intuitively. But what is the sweet spot? Where do I cut off, right? If I want compressive recognition, and also that how many, so far compressive sensing is really about how many measurements you needed to recover a signal. But what about recognition? Recognition, we're interested in the different characteristic of a signal, right? Maybe we need much fewer measurements under certain situations. We don't know that. There's no theory to give us any idea. So if you're interested in this, we have a paper to appear on the PAMI called Robust Space Recognition by Sparse Representation. Also, there's another companion paper sort of explain more of the theoretical aspect of it. We submitted to information theory. Both are downloadable from my website. Those are the folks gets involved in this. And just before I leave, and it's just some of the follow-up things, how sparse representation can be useful. This is going to appear in the CVPR this year. That we did a very simple test, just that look at super resolution is sort of a natural sparse representation or compressive sensing problem, right? You start from low resolution image, try to recover a high resolution image. So that's something obvious for us to try. So we did that. So basically, high resolution. Suppose that your high resolution image patches can be written down as some dictionary D you given to you. You try to recover it through alpha, but imagine you try to recover the same alpha from a downsampled image. Right. Once you find the same alpha, you go back to the high resolution patches. You can recover Y. So that's really a very, very simple formulation of super resolution, the problem. So we took. Turns out that the message is very surprising for very generic image like this. So we can get a much better performance despite using a much smaller random dictionary. So we take some images from the Google, just random search, draw patches. We don't even learn anything. Just draw some patches. And then we compute a sparse representation. So we use a much smaller set of dictionary. It's about 10,000 patches, much smaller than the traditional machine learning-based techniques for super resolution, like Bill Freeman's work. He uses millions of patches to try to learn some statistic, then to do super resolution. Actually, the results is much worse. So you can see that the results and compare. This is magnified by 4. So you can actually see that the results is quite impressive comparing to. And also, we did also do motion segmentation because one of the things in multiple view geometry, we know that the tracked features associated with each motion lies on low-dimensional subspace. So therefore, you can potentially use this to cluster the data. Or if some of the feature gets mistracked, again, you have to correct the error, just like a robust scenario, right? So you try to, for each tracked trajectory, you try to find the coefficient and then correct the error. It's the same problem, but here, because the structure of the motion data probably has some amazing structure, for this Johns Hopkins 155, we did it very soundly. This is a spectral clustering-based method, LSA. This is local subspace alignment using spectral clustering. This is actually a Cartani's multi-stage, essentially EM algorithm. But using the compressive sensing type of techniques, you can get much, much better performance. And also, those techniques do not work at all if you start to throw in outliers or mistracked features. Here you can handle, the surprising message is that you can handle, with the database almost 80% corrupted, surprisingly robust. You still can clustering the data very well and repair the missing tracked features. Very, very surprising. And also someone else, not us, but actually we post our paper after we submitted PAMI, and someone immediately took it and implemented to speech recognition. So they tested on, also this very, very surprising, they tested on using the Aurora data sets for digit, correcting the error and classify single digits. Such the state of art at the -5 dB, which is very, very challenging, signal to noise, signal to noise. And actually the performance is like 60-some%. And using just trivial L1, they actually code, they repeat exactly what we did, and they actually post the code online. So there is a link you can check. And actually can boost the performance up to 90%, very, very nicely. So you get a significant boost of the performance for a very challenging speech recognition problem. data sets. So this is sort of quote, so summarize, what really the gist of the work is really trying to use a very simple algorithm, very simple tool, hopefully to deal with a challenging problem in computer vision.
Thanks, our speaker. Any additional questions?
So I hope some of the things answered some of your earlier questions. So if you want to know what really face recognition is about, the mathematics is this one. So you can summarize the setup as finding a needle in a haystack on the tip of a needle. That's really the mathematics behind this problem. It's very neat because if you can calculate all the face images, even you can collect hundreds of faces. But if you normalize them to one and computing how much volume this span on the sphere, 10 to minus 60 something. It's nothing. The volume is just tiny little bit. And you actually try to give an image, particular face, lying on the needle, which is essentially a K facet on that needle. And there is a cross pointer with correcting all the errors for you. And so really, so far, there's really no, we're still doing some the analysis. We have some work with John Wright in preparation. In fact, in this case, we can actually nearly show that this is precisely the situation allows you to do sparse error correction, dense error correction, sorry about it. This is a situation, this is a mathematical model allows you to handle 80 or even 90% of gross errors easily. So in fact, the theoretical bound we calculate is 98. So for the data sets of face data sets.
What doesn't include, right, is sort of invariance in the features.
Yeah, so
right,
the
so
pose is another issue. We are trying to...
Right, so not just pose, but expression, misalignment, even the...
So for experimental empirical expression handles very well because it is robust. So it's treated as occlusion. So use the rest of the face to do recognition. But maybe it's not scalable, as you can probably imagine. If you have a large database, then the scalability may become an issue. You have to design specific tools to deal with expression. So that's the issue.
FRBT and seems to be going, the best performing techniques are really addressing that misalignment question, either by embedding in the features or sort of maybe really registering really accurately.
Yes.
And I don't know how, I think this is great. I think it's, so maybe solves half the problem, but it's sort of the occlusion, what measurements do I want to trust, which ones do I want to throw out?
Yes.
Question.
So even alignment matching itself is, you needed to have robustness built in. So how to do that correctly? That's, but again, that's actually a problem we're working on. We're really working on trying to tackle what is additional problem component and brings in by pose. So either invariance of domain or local versus global. How much then illumination is global, but the deformation is local. How do you actually balance that? What is the best way of dealing with that? So in a sense, I'm hoping that we try to isolate the problem better so that we can potentially eventually we will be able to learn a lot of lessons and then putting things together more nicely, rather than start from the very beginning to compound and conquer. Try to design a system that addresses all the factors, right? So that's I think the.
Data I want to trust, what features do I want to throw out, and so on. But there is this other half of the problem, right?
Well, yeah, nobody. I don't think we do not even set out to solve all the problems with face recognition. Just trying to make a simple point with one very specific, well-defined problem. Hopefully that we can move on from there more. We have a baseline to compare.
Like in ID identification phase, in the identification case, you may just have one registration file for somebody. So now you have now in the airport or building, you recognize that person based on only one training image. So in that case, the
so that's actually we have been experimenting. my personal feeling is that right now I don't think that is quite a well-defined problem in the sense that maybe you're asking the impossible. We have tested something with the Pi database. You can even just use a very few training data. If the lighting conditions are similar, you can, for feature matching, can do very, very well with recognition. But once the lighting is off, everything went crazy. But then if you want to deal with lighting, just like this method shows, you really need the multiple training data, training images. You have to see what you're trying to decide upon. You cannot do sort of ask the impossible. There are information that if it's not in your training data, you cannot really recognize it.
Also, right? Because you still
it's challenging.
If you know the face, then you have 3D information, right? To input the lighting.
Yeah. So, but bringing 3D is another kind of worm, right? So that then the registration and how to get the 3D accurately, and how to align the face, the 2D images with the 3D. That's that's probably not just single kind of worms, probably multiple kinds of worm. So.
Yes. Actually, it's still in alignment.
Yes, so, but it's much more robust. You can actually see some of the
requirements.
So you can see some of the results. It's actually, I'll show you what the alignment does. If you see this case, this woman gets corrected. So you can see that there is a white boundary here. It gets corrected as occlusion. Basically, there's at least several pixels of misalignment with the training and testing. Actually, even the training themselves are. So our feeling is that at least for training, you should align them as well as possible, right? So if the training are not even aligned, that then the whole linear models fall apart. So, but even in this case, it can handle at least if there's some robustness built into your system, you can handle it. But you should not expect it to scale up. If you want this to scale up, you better align them well. Even for fingerprints, right? You have to align them well. Otherwise, how the heck are you going to recognize anybody?
Supervised questions, like I don't want to do ID, but I just want to do clustering on, have 1,000 images of faces.
Yes.
I mean, that's a pretty interesting problem.
Yeah, so that's, as I mentioned earlier, that we have worked basically, it's exactly the same principle. You compress the data using the no-dimensional structure. There is a website on my website that called the lossy compression-based method. In fact, it's very, very effective. If you have reason to believe that your data has a piecewise linear structure, Gaussian or linear structure, even if they are degenerated, which is the case with high-dimensional data, you should give that method a try. So far, that is the one giving actually the state of art for image segmentation and also give the motion segmentation. Far better than spectral clustering, actually. And also, the one thing you get more from it's a generative method, right? So you actually fit the cluster. Unlike spectral clustering, it's discriminative. So for generative model, the really nice thing about it, you automatically get a lot of structure out of it once you cluster them. And also the objective, you start with the clustering, corresponds very nicely with the structure you find in the end. It's entropy and the dimension of the data and so on. And also even the noise, the amount of noise in your data, you find them automatically. Right? Using spectral clustering, after clustering, you still have a lot of bookkeeping, a lot of things to clean up to do. That's something we can talk about, separately if you're interested.
Okay, let's thank Yi once more.
Thanks.